magnetized coronae and stars and accretion disks.
Okay. Good afternoon, everybody. Today I would like to share with you some physical ideas about the nature of magnetically active coronae of stars and accretion disks. Here is a brief outline of my talk. After some introduction to magnetized coronae in various astrophysical environments, I will present a statistical description of a magnetically active corona above a turbulent accretion disk. I will argue that one needs to develop a statistical approach to describe the magnetic field in the corona. And we'll devote some time to explaining how we think this should be done. This model will highlight the importance of magnetic reconnection in the formation and the structure of the corona. And this will bring me to the second part of the talk on reconnection, where I will first sum up the recent progress that was achieved in the field of magnetic reconnection in the past, say, 15 years. And then we'll use the new understanding of reconnection that could be derived from all of this work and to apply it to various astrophysical environments. First, I will derive a simple, although very approximate, but I think very useful criterion that one can use in order to tell whether fast reconnection is possible in a given physical system. And then I will apply this to several astrophysical situations in which we think magnetically active coronae are present. First, I will consider the very old problem of solar coronal heating, and will present a line of arguments showing that the corona ought to be considered as a self-regulating, marginally collisionless system. I will define what I mean by marginally collisionless in the course of my talk. I will then present some observational evidence that coronae of other stars probably also satisfy the condition of marginal collisionality, and also perhaps even accreting black holes, again, are found in a state observationally that implies that they are marginally collisionless. If I have time at the end of my talk, I will say a few words about what this fast collisionless reconnection condition means for magnetically dominated engines, central engines of gamma ray bursts. All right, so first, well, the archetypical example of an astrophysical corona is, of course, the solar corona, and you must have seen similar pictures and movies a million times. The corona is described as a very hot gas of order millions of degrees Kelvin, situated above the solar surface, and it dominates it is responsible for the X-ray emission of the sun. This gas, however, is very tenuous. The density here is very low, so this environment is dynamically dominated by the magnetic field. The typical parameters of the corona are such as this, but in some sense, it's not really useful to talk about typical parameters because the corona is highly inhomogeneous in both space and time, and this is a very important point. And of course, this picture demonstrates it beautifully, the inhomogeneous nature. Now, coronae, powerful coronae are also inferred observationally to exist around accreting black holes in both galactic sources, stellar mass black holes, and in active galactic nuclei with supermassive black holes. So such as this one, this is an image of an AGN obtained with the Google Space Telescope. But this one is an actual spectral data obtained for a Cygnus X1, which is one of the most important, very first objects to be studied in our galaxy. This plot shows actually several curves, as you can see. These are spectra of this object corresponding to different accreting states. And in some of these, such as this one in red, you see that most of the power comes in the relatively cold component that is associated with the accretion disk. But sometimes there are states where most of the power comes out in much harder energies, for the 100 keV. And furthermore, even for this so-called high soft state, there is also always some sort of hard X-ray tail that needs to be explained. This emission in this range cannot be attributed to the disk itself because the temperature of the disk is maybe a few keV. And it is usually explained as a result of comptonization of the soft disk photons in a hot corona lying directly above and below it, as in this sandwich geometry as was proposed by Liang and Price and Bisnavata, Kogan, and Blinnikov a long time ago. Now, from the very early days of research on accretion disk coronae, people have invoked and used the analogy with the solar corona. And they did. I think it's a very valuable analogy. And there is some common physics that underlies the formation of any magnetically active corona in astrophysics. And let me describe for you how it works. Basically, one starts with a relatively cold and dense medium immersed in an external gravitational field. And this medium is turbulent for whatever reasons. There is some mechanism for driving turbulence. And in 3 dimensions, this medium, of course, is cold, but it's still hot enough so that it's completely ionized, and or at least partially ionized and conducting. And therefore, it is described by the MHD equations. In 3 dimensions, MHD turbulence produces magnetic fields through dynamo. And importantly, because of the gravitational stratifications, some of the magnetic flux ropes in this medium rise up buoyantly due to Parker instability and emerge into this much lower density region above the above this medium. And importantly, a certain fraction of the magnetic energy, energy released by this turbulence is not dissipated locally here, but is transported as Poynting flux into this overlying corona. And it is dissipated in the corona through magnetic reconnection events, episodic discrete events. And since you take a certain amount of energy and give it to a relatively small number of particles, the resulting energy per particle is very high. That's why this corona is very hot. So that's the picture of why there is a corona and how why is it hot compared with the underlying medium. Now, most of the previous research on accretion disk coronae have focused on trying to match the spectra, that is, on the properties of radiation and gas. And this is obviously due to the fact that we cannot see the magnetic field directly. We see radiation and gas, but we cannot observationally infer anything about the magnetic field. However, I think it makes sense for us to think about how this magnetic field looks like before we can sensibly approach any of the other questions. This is simply because the magnetic field is the dominant agent in the corona. So this provides us with the motivation to study the magnetic structure of an accretion disk corona. Now, however, if the disk is turbulent, the magnetic field is not a large-scale uniform or ordered magnetic field. It is highly chaotic and driven all the time by flux emergence from the disk and by turbulence in the disk. So we have to build a statistical approach. And there is a number of questions that we wish to address. For example, how are magnetic structures in the corona distributed with respect to the sizes, and the magnetic flux they carry, and so forth? Right? Is there an inverse cascade that leads to buildup of a population of large loops? How much magnetic energy is pumped into the corona from the disk? how is this magnetic energy distributed with the height above the disk? How is magnetic dissipation distributed with the height above the disk? Furthermore, if you have loops like this connecting two parts of the disk, they will transfer angular momentum. And of course, in accretion disk theory, the angular momentum transport is one of the most important problems. So we want to understand how important is this angular momentum transport due to the coronal magnetic field as opposed to the internal magnetic fields in the disk itself. Now, if you want to address the connection of this corona with large-scale outflows, such as winds and jets, they usually require open field lines. So we want to understand which fraction of the field will be open at any given time. And furthermore, how the answers to all of these questions depend on the magnetic reconnection. So to address these questions, I'm trying to build, in collaboration with Jeremy Goodman at Princeton, a statistical description that actually follows on the footsteps of a previous work by Taut and Pringle that was done 12 years ago. But our model includes much more realistic physics and also goes much farther in things that can be calculated within it, in predictions. The basic approach can be described as follows. We represent the corona as a statistical ensemble of loops such as this that have two foot points on the surface of the disk. And for simplicity, we assume that the magnetic flux within each loop is the same, is constant. And then each loop is described by a certain number of primary parameters, which we choose to be its radial foot point separation and the azimuthal foot point separation. Or equivalently, the length, the distance between the foot points, and the orientation with respect to the toroidal direction, say. So these are our elementary magnetic structures that we want to work with. We then formulate the equations of motions for these loops in this delta r, delta y parameter space, and introduce the distribution function in this parameter space, and write down the kinetic equation for this distribution function that is similar to Boltzmann's kinetic equation for the atoms in a gas. Then we solve this equation numerically to obtain a statistical steady-state description. Once we have that, we can compute various integral quantities, such as the overall amount of magnetic energy in the corona, the torque transmitted, and so forth.
Magnetic fields or the fluxes to these loops are all the same, or are you very?
So to keep them in general, one should consider a distribution of fluxes as well. For simplicity, we just keep them the same.
And then you know something about how much you can bend those flux tubes given the feedback gravity forces.
Right. So here I might talk a little bit about this. I can actually discuss this now if you want, but I'll try to be brief. So in principle, we consider, or eventually we will consider, a self-consistent atmosphere where the shape of each loop is determined by the pressure balance between the magnetic field inside of this loop and the ambient pressure. And the ambient pressure is a function of height. So it's just one function. But in reality, we think of it as a combined pressure of all the neighboring magnetic loops. And that pressure, in turn, is a self-consistent mean field that you have to compute from the distribution function. Now, in general, when we think of the system like this, we are interested in spatial scales much larger than the thickness of the disk, which is assumed to be thin, but probably much smaller than the radius. So in this sense, the accretion disk problem is simpler than the sun, because here we have a good separation of scales where we can apply this theory. In terms of time scales, we're interested in time scales longer or maybe comparable. Well, if you're interested in steady state, it has to be longer than the orbital time scale, but obviously much shorter than the overall accretion time scale. Now, yes?
How do you enforce magnetic rescue conservation? Or is that important?
Well, it doesn't appear in our equations. Well, you'll see, because we are not solving MHD equations. We are building qualitative description of the system in terms of the elements that we think are the most, and processes that we think are the most important. For example, we choose loops because in the solar corona, all you see is loops. I mean, you don't see any other structures, basically, other than loops. Our loops, for simplicity, have no internal twist. So all the currents, this is a force-free corona, so there are currents in the corona, but they constrained to flow on the boundaries between loops, basically. Now, what are these processes that we think are the most important in the system? First of all, there are several processes that, on average, increase the magnetic energy in the corona. They make the coronal field depart from the potential field and make it non-potential. These processes are as follows. First, there is just emergence and sometimes submergence of magnetic loops from the turbulent disk into the corona, and this happens at small scales comparable with the disk thickness. Once in the corona, the loops are stretched by Keplerian shear, which is a very important process in the accretion disk physics, but obviously not as important in the solar physics. And also, since the disk itself is turbulent, the foot points of the loops will undergo essentially a random walk on its surface. That will result in some effective diffusion. Now, in addition to these processes, if one wants to get a sensible steady state, there must also be a process that releases the stresses that are built up, that dissipates energy and brings the field closer to the potential state. And this process is magnetic reconnection between loops. It is also important because it is the only process that can efficiently produce a population of loops with large radial foot point separations. That is, if you start with a small loop, Keplerian shear will increase its azimuthal foot point separation, but will not affect its radial foot point separation. If you want to have loops that connect different radii, you can only do it by reconnecting between loops. And all these processes occur on various spatial and temporal timescales over and over again. And I would like to think of the corona as some sort of boiling magnetic foam, with loops rising, expanding, and reconnecting. As a final result, we obtain this loop kinetic equation for the distribution function of loops f. And it has several terms. The source term here basically describes the flux emergence at small scales. Then there is the diffusion, which is in general anisotropic, that describes the random walk of the foot points on the surface of the disk. The third term is Keplerian shear. It's one of the most important terms, but it's actually easiest to describe mathematically. It's just advection with the velocity delta y. Y is the toroidal direction here. So the velocity delta y dot is proportional to the radial foot point separation. And then finally, the fourth term is reconnection between loops. This is the most non-trivial, most difficult term to describe, so I devote the next slide to it. We describe reconnection in a way similar to binary collisions between atoms and a gas. That is, two loops like this can come together and reconnect at this point here. As a result, they form two new loops, this one and this one. So in this picture, the total number of loops is conserved. Furthermore, if this reconnection process itself is rapid compared with the characteristic timescale for these foot points to move around, which is the orbital timescale, then during this process, the foot points basically stay put where they are. And this allows us to formulate the reconnection rules that determine the properties of the product loops in terms of the foot point separations of the incoming loops and also the impact parameter of this interaction. So it's similar to the way one uses momentum and energy conservation to describe collisions, binary collisions between particles in a gas. And then again, once we have this binary process, the overall effect of it on the distribution function is basically captured with a collision integral, with a nonlinear integral operator similar to Boltzmann's collision integral. It has two terms. It has a sink term and the source term, the quadratic and the distribution function. And this quantity Q here is the rate at which reconnection events between loops of two kinds, A and B, happen per unit time, per unit area on the disk. On general grounds, this quantity is proportional to the orbital velocity, because all the other processes are proportional to orbital velocities. And the cross-section for this interaction. This cross-section depends on what kinds of loops are there and what is the impact parameter. Basically, larger loops have larger cross-sections, and we have a way of calculating it. And then the overall efficiency of this process, the overall efficiency of reconnection, in some sense normalized to the Keplerian shear, is quantified by this dimensionless parameter little q that we put here. And we wish to investigate how properties of the resulting steady-state distribution depend on this parameter q.
So the number of loops is conserved only if the loop never intersects itself, right?
Only what?
Only if the intersection is never between a loop and itself.
Right, because in this picture, we don't have twisted loops. As I said, we don't have currents flowing inside of the loops. What it means is that there is no internal twist in the loop, and so the loop stays in one plane. It doesn't intersect itself.
But are your loops growing in size?
They are. A given loop changes its foot point separation, say because of Keplerian shear. And as it does, it grows in size also.
Means it's two loops will reconnect only if they cross physically.
Essentially, yes. Or, well, actually, that's a question that within this model we cannot calculate this. Or after they reconnect, they have to move to the new shape, the new equilibrium shape. And on its way there, they will be crossing other loops perhaps as well. Now, but given this equation, we can numerically solve it. And then we obtain a steady state distribution. This plot, for example, shows two cases with two different values of Q. First, first let me say this, that what I plot here is in log-log coordinates, the distribution function, versus the length, that is the distance between the foot points, for different orientations. So first of all, if you just switch off Keplerian shear, you expect your distribution function to be isotropic, because this reconnection process doesn't care about the absolute orientation of loops. It only cares about the relative orientation and position. And indeed, in this case, the distribution function is isotropic. That is the same for all values of theta. Theta is the angle with respect to the toroidal direction. And it's described by a power law. Now, if you decrease this value of Q, which means that you decrease the role of reconnection with respect to Keplerian shear, you expect your distribution function to become more and more anisotropic, because loops are predominantly stretched toroidally. And this is indeed what we find. Purely toroidal loops, theta equals 0, have now shallower distribution, and purely radial loops have a much steeper distribution. In this problem, physically, we don't have a characteristic length scale. Here we are talking about length scales much larger than the thickness of the disk. The thickness of the disk in this unit is 1, which means 0 in logarithm, right? So for large distances, there is no other scale. That's why we expect power laws, and indeed, that's what we get. And in general, the distribution function as function of L and theta is described by a power law in L with the exponent that is a function of the angle. Now, once this is obtained, we can compute the total magnetic energy in the corona, for example, the total angular momentum transported by these loops. And what we find, and it's not surprising, is that as reconnection becomes more and more difficult, and the other way to say it is that Keplerian shear becomes more and more important, both the total magnetic energy in the corona and angular momentum transport increase dramatically up to certain, after a certain, this value of Q, as it decreases, at some point the total energy starts to increase. We have an explanation for this. The bottom line here is that understanding reconnection is important if one wants to understand anything about accretion disk corona. If you suppress reconnection, okay, let me describe it here. So one can see that whether or not you have reconnection is important by considering these two extreme examples. In one case, imagine that the gas here has very large resistivity. So reconnection happens easily. In this case, your magnetic field will never be very different from the potential magnetic field. And if your sort of magnetic structures are concentrated at the disk surface on the scale of order h, the thickness of the disk, the characteristic magnetic scale height for the potential field will also be of order h, in which case the total amount of magnetic energy will be relatively small, and the total amount of dissipation will be small. Now, one can also consider the opposite extreme when reconnection is strictly prohibited, when you have ideal MHD. What will happen then? Then magnetic loops just get stretched and stretched, and as they do, they grow. Eventually, they open up. At this point, the magnetic field will effectively look like a forest, a dense forest of open field lines going up and down. The total amount of magnetic energy here will be very large. But of course, since we explicitly turned off dissipation, there will be no dissipation. So there will be no coronal heating, essentially.
Which one's more efficient with angular momentum transport?
Actually, in terms of the angular momentum transport, both are not efficient. More efficient case would be in between. The reason why this is not efficient is, well, in this case, you would get a contribution maybe comparable, somewhat smaller probably than that comes from the disk itself, right, in this case. In this case, it's actually very interesting. As loops grow, as they reach a height comparable to the radius of the disk, the character of this inflation changes qualitatively. And it changes in such a way that it speeds up, basically. So the loops will open on a finite time. And as they do, the field, say the toroidal field on each of these field lines will become zero, will go down. And therefore, the torque will also go down. The most efficient case is in between.
You have no reconnection, so how do you get open field lines? You have no reconnection.
That's right.
So how do you get open field lines?
That's very easy. You don't need reconnection to get open field lines. You need reconnection to close them back.
Close an infinity track.
They are going out to infinity. That's right. Yeah, that's right. Yeah. That's actually a good question, and that is the reason why I drew this line here, sort of to show that at a given height, if you fix at a given height, then you can think of it as open. In reality, of course, they close very far. Yeah.
You just said that as these inflate and open up to infinity, they lose their toroidal component.
Mm-hmm. Because the toroidal.
They reconnect, they don't torque the underlying material.
Sorry.
And as a consequence of that, when they reconnect far away, they don't torque the underlying footprint, and thus don't transfer angular momentum.
When they reconnect far away, they don't reconnect far away.
They don't.
Yeah.
Okay.
But
So
yeah.
then what you're saying is the reason why it's inefficient when they open up is
Yeah.
that they don't reconnect.
No, the amount of angular momentum the field removes is, strictly speaking, equal to the vertical field times toroidal field, right? It's the toroidal field that talks. Right, and the toroidal field goes down. That's what.
The one then you have a chance to connect parts of the disk with very different radii. And so there are two ways to generate a toroidal component to the field. Either you still have it when the field's buoyant, or you reconnect this radius to this radius, and then the shear between the two creates for you a toroidal component to your field. And that's where your maximal stress comes in. So it doesn't happen immediately at the reconnection event. It's not like the
No, angular momentum has nothing to do with reconnection events itself. Angular momentum transport is, right?
I'm thinking the other way around. I want to understand how the reconnection affects the angular momentum transport a bit.
Okay, I will be happy to talk about this. I have two subjects to cover. So this is the end of one, and I still have, it's actually a very rich problem, and what I'm presenting here is just some small kind of highlights of it, but there is much more to it. It's actually very interesting. I mean, I can try to answer briefly to this. If you have a loop like that, it will have a certain amount of toroidal field that is related to how much it gets stretched in the toroidal direction. If you plot the toroidal field as a function of the distance between the foot points in the toroidal direction, it will first grow. If you start with a purely radial loop, it will first grow continuously until the height of the loop and all the separation reaches a fair fraction of the radial distance, of the radius of the disk. Because at this point, it's no longer plane geometry like we assume here, it's axisymmetric geometry. Then the opening becomes faster, and you'll have larger volume available to you at larger distances, and most of the toroidal twist, most of the toroidal flux will be concentrated there at large distances. What it means is that the toroidal field near the foot points will become small, and as a result, the torque will be small. But we can talk more about this. Now, but let me now switch gears. I have much more things I need to say. And talk about reconnection. In astrophysics, reconnection is a magic word that is invoked whenever needed. And in fact, there is a preferred mechanism for magnetic reconnection that is used in astrophysics. And it has to do with waves, with a certain type of waves, in fact, called hand waves. And it goes as follows. We know that fast reconnection happens in the solar corona and the Earth magnetosphere, and so it will happen in whatever astrophysical system that I'm studying. Now, this reflects a common perception that exists in astrophysics, that we don't know anything about reconnection, and so we are free to assume anything we want. I will argue that this is not quite true, and in the past, say, 15 years, there has been a lot of progress, basically with the advent of powerful numerical simulations and dedicated laboratory experiments, that we still, it is true to say that we still don't know everything about reconnection, but we now know some things. And in this talk, I will try to use only those things, only those facts, which I believe to be relatively firmly established, on which there is a consensus. So let me say what we know about magnetic reconnection. First of all, reconnection is defined usually as a rearrangement of magnetic field topology, which is illustrated here. You have regions with different topologically distinct regions of magnetic field, and reconnection means transfer of flux from one region to another. So field lines come in from here and here, they reconnect at this central X point, and then they move out as these lines, here and here, right? The reason why reconnection is important, believed to be important in astrophysics, is that it often is accompanied by violent release of magnetically stored energy and its transformation into various forms of plasma energy, such as this. Now, the reconnection research, started actually a long time ago with the Sweet-Parker theory that was proposed to explain solar flares. And in order to talk about reconnection, one has to understand this model first. And that's why I would like to take you through it. in ideal image D, reconnection is impossible. Therefore, if you want to have reconnection, you have to go beyond the ideal image D. And logically, the very first thing to try is resistive image D. This is exactly what Sweet and Parker did. In this model, there is magnetic field reversing across this midplane, right, of strength B naught, going this way here and that way here. And according to Ampere's law, this implies a layer of strong current into the board. This high current density is needed to make the resistive term important inside the reconnection layer, because usually the resistivity is small, so you need very high current density. Now, what happens here is as follows. Plasma enters this layer from both sides with some reconnection velocity, Vrec. And then this point is the X point for the magnetic field structure. And it's also a stagnation point for the flow. So the plasma has to move out along the layer to the right and to the left. And the goal of the theory is to determine this reconnection velocity, the thickness of the layer, in terms of the global parameters, such as the global length, L, the reconnecting magnetic field, B naught, and of course the resistivity. And this is fairly easy to do. One just combines a number of basic equations. First, Ohm's law basically tells you that the rate at which the magnetic flux is brought into the layer is balanced by the resistive diffusion out of the layer. That gives you this. The equation of motion yields this fact that the outflow velocity, u, is essentially equal to the Alfvén velocity computed with the upstream magnetic field. And finally, the mass conservation, at least in the incompressible limit, basically requires that the amount of plasma that enters the layer has to move out. It gives you this. And combining these three relationships, one immediately arrives at this famous Sweet-Parker scaling that says that the reconnection velocity normalized to this Alfvén velocity scales the same way as the inverse aspect ratio of the layer and scales as 1 over the square root of the Lindquist number S, which is like the magnetic Reynolds number, which is like the Reynolds number, except that velocity is replaced by the Alfvén velocity and viscosity is replaced by the resistivity. Now, usually this Lindquist number in astrophysics is very large. For example, for parameters typical for the solar corona, it's just huge. It may be 10 to the 12 or more. And if you just plug it in, you'll see that the Sweet-Parker reconnection timescale is very long. It's for several months, which is much, much longer than the observed duration time for flares, which is like 15 minutes. So it was realized from the very start that Sweet-Parker reconnection is too slow to explain solar flares. The situation changed in 1964 when Petschek came along and proposed a modification to the Sweet-Parker picture. He noticed that the reason why the Sweet-Parker reconnection rate is slow is that one needs to strike a balance between two opposing needs. On the one hand, you want to have a layer that is thin enough so that resistivity is important. On the other hand, you have a bottleneck for the flow. Because if the layer is thin enough, all the matter that enters it has to fly out through this very narrow channel. That's difficult to do. So he suggested that it may be that these two scales for current concentration and for the outflow do not need to be the same. And he proposed this picture, which has, unlike the Sweet-Parker model, has some structure to it. At the center, there is a very narrow and very small diffusion region, which is indeed like the Sweet-Parker reconnection layer. And attached to it are 4 standing shocks like this. And these shocks deflect the outflow this way. And as a result, the overall reconnection rate could be much higher. In particular, in his model, he predicted that there is a family of solutions with parameterized by the length of this layer, say normalized to the overall global length L. So if this length delta can be, capital delta, is much smaller than capital L, then the reconnection rate may be much higher. And he derived an upper limit on how high it can be and showed that it scales as 1 over the logarithm of the Linkus number. And this is fast enough to explain solar flares. So everybody was happy with this model for a while, for the next 20 years, essentially. But, OK, let me just say a few words. In astrophysics, Paycheck model is important because astronomical systems are usually astronomically large. And the global length L is usually much larger than any of the microphysical scales. And therefore, for any kind of physics that you have inside of the layer, if your overall geometry is a long and narrow Sweet-Parker-like current sheet, it will be too slow to have any relevance for observations. So you have to have some sort of geometric enhancement, like in Paycheck model, to have fast reconnection. Now, however, unfortunately, numerical simulations and also some analytical arguments and even recent laboratory experiments have shown that in resistive MHD, when plasma is collisional, Paycheck model just doesn't work. Even if you set it up initially numerically, it will collapse promptly into a long and narrow Sweet-Parker-like current sheet, and the reconnection will be slow. So this all suggests that in resistive MHD, there is no fast reconnection. The natural question is the fast reconnection in collisionless plasmas where resistive MHD doesn't apply? And the answer to this question appears to be yes. Furthermore, there are 2 candidates for fast reconnection in collisionless plasmas. There is whole MHD, so-called whole MHD, and 2-fluid reconnection, and the anomalous resistivity reconnection. And both are very interesting, and I would be happy to talk about them, but probably after my talk. I don't have time for this. Both of them have been, signatures of both of them have been observed in the MRX experiment. At the moment, we still don't know which one works under what circumstances and how they interact with each other. But at least it's good to know that we have 2 of them, so one of them will work. So it does appear that collisionless reconnection is fast. And this is a numerical demonstration of this. This is a simulation done by Paul Kasek and others where they had both Hall term and resistivity. And when they had relatively large resistivity, so that the Hall term was not important, they obtained the Sweet-Parker reconnection layer with slow reconnection rate. And then they turned the resistivity down below some certain threshold, and the system immediately switched into the fast reconnection configuration. Now, how we can quantify, how we can distinguish for a given physical system whether it will be in the fast or in the slow regime. To do this, you have to compare the relevant scales. The characteristic scale for collisional resistive reconnection is the Sweet-Parker thickness. And for collisionless reconnection, it is usually the so-called ion collisionless skin depth defined here. And then the condition for reconnection, for fast reconnection, is simply this, is that delta Sweet-Parker has to be smaller than di. This is indeed has been confirmed in the MRX, where this plot shows essentially the reconnection rate scaled to what one would expect for a Spitzer resistivity, for Sweet-Parker with Spitzer resistivity, versus this collisionality parameter, the di over delta Sweet-Parker. And you can see that if delta Sweet-Parker is larger than, say, 2 times di, the result is consistent with 1, and it's small. But then when the plasma becomes collisionless, the reconnection rate increases dramatically. So we now need to take this condition and try to take it further, express it in terms of basic parameters of the plasma. That's actually pretty straightforward because we know what all these things are. And furthermore, since we're talking about collisional and collisionless, it would be nice to express the results in terms of collisionality, in terms of the mean-free path. And the mean-free path comes in through the resistivity here. And it's straightforward to show that the ratio of these 2 scales basically scales as the square root of L over the lambda mean-free path. And so the condition for fast collisionless reconnection can be simply cast as follows: that you'll have fast reconnection if the length of the system is smaller than about, say, 40 times lambda mean free path, the square root of the mass ratio. We can take it seriously and take it further. We know what the mean free path due to column collisions is. It's a function of density and temperature. And then the question is, what is the temperature at the center of the reconnection layer? This is what is important here. And I can present arguments showing that this simple estimate is actually a good estimate. Substituting it here, we'll immediately get this final form of this collisionless reconnection condition that relates the global length of the system, the ambient density, and the magnetic field. If there is a guide field, it will be modified by another factor here. But that's basically the condition, and I think something like this condition will need to be used to build a prescription for reconnection as a subgrid model for numerical simulations. Now let me go to applications. And of course, I have to say that deriving it, I ignored all factors of order unity. So it's not a rigorous condition. Now, in the solar corona, there is an old outstanding problem of the solar coronal heating. And the leading explanation is the nanoflare model due to Gene Parker. The basic picture is that coronal loops emerge, similar to what I described for the disk. Coronal loops emerge from the surface of the sun. They get twisted by continuous foot point motions. And that creates current sheets, sets up current sheets in the corona. The energy dissipates through reconnection in these current sheets. And that results in coronal heating. Now, it has been realized relatively recently that, well, I guess maybe for a long time, that the problem of coronal heating is not as much a problem of raising the temperature of the gas, but it's the problem of raising the density. It is very important to understand in any corona that there is the mass in the gas in the corona comes ultimately from the surface of the sun or from the disk. So the mass exchange is very important, as you will see in a minute. So the question is this: you have certain bunch of loops that may be described by some statistical theory, such as the one that I described previously. They come in a range of sizes and magnetic field strength and so forth. And these are all determined by the dynamics of these loops. Now let us ask then, what determines the density? Why is the density in the solar corona of order 10 to the 10, say roughly speaking, particles per centimeter? Why is it what it is? So my main idea is that coronal heating should be seen as a self-regulating process that keeps the density at high enough level so that it's marginally collisionless. And here is why. You can take that condition for fast collisionless reconnection and rewrite it in terms of density, say. So you can define a critical density in terms of the magnetic field and the length of a given structure, of a given reconnection layer. And notice that the number that you get for reasonable choices of B and L is kind of comparable to what is actually observed. And remember that this equation was derived just from some physical arguments with no knowledge of the solar corona. So I don't think that's a coincidence. I think there is a reason for this fact. And the reason is as follows. Imagine the following example. Imagine that you have a reconnecting layer somewhere set up in the corona. And let's say it has a certain scale, L, and certain magnetic field, B naught. And let's say that initially the density of the plasma is higher than this value. What will happen then? What will happen is that reconnection proceeds in the slow Sweet-Parker regime, and not much energy is released. So the system just sits there doing nothing. But it gradually cools by radiation. radiative cooling is important in the corona on the time scales of order 1 hour, say. So on this time scale, the plasma cools, and as a result, it precipitates down to the surface. And at a given position in space where this current sheet is set up, the ambient density will go down. At some point, it will go below this number, and the system will switch rapidly into the collisionless, fast collisionless regime, and the flare will commence. As a result, a certain amount of energy will be released in the corona. And now it is important to understand what happens to this energy. What happens to this energy is the following, that there is a very important feedback effect here. Since most of these field lines are closed field lines, the energy that is released somewhere in the corona will be transported by energetic electrons, by essentially thermal conduction, down to the surface of the sun. And will be deposited there in the foot points of the flux tube that just underwent reconnection. A certain fraction, large fraction actually, of this energy will not be radiated away, but will cause evaporation, known as chromospheric evaporation, that is observed in the aftermath of solar flares all the time. So it's a very well-known effect. This chromospheric evaporation will fill this flux loop or flux tube with hot and dense plasma. And that may raise the density above that critical value, and then a subsequent reconnection involving this flux tube will be suppressed until, again, it cools down gradually on the radiative timescale. So in this sense, and of course in some statistical sense, the corona is a system that works itself, that works to keep itself roughly at some critical marginally collisionless level. But of course, it's highly intermittent and inhomogeneous. And this is the self-regulating mechanism for coronal heating. I also believe that similar processes work in the coronae of other stars and accretion disks. Well, I know that I'm running out of time. So for other stars, I'll just show you there has been observational evidence based on the work by Kasek, Mulan, and Shea just recently, where they took a sample of 37 stars, both sun-like and them dwarfs, and something like 100 flares observed in these stars. And for each of them, they used some sort of model that people use in this stellar X-ray astronomy business to derive the properties of the plasma there for these flares. From that, they estimated the uncollisionless skin depth and the Sweet-Parker thickness and plotted it on this graph. And you see that it actually correlates very well, which is surprisingly well, I think. So it's what comes in here, well, this model, I mean, there is actually a lot of assumptions in the model they use to derive all these numbers. You need this field strength, you need density and temperature, and the size. The size is, so this is all obtained from the emission measure and the duration of the flare, essentially, things like that. I mean, you can ask whether it's correct or not, who knows. It is amazing. Yeah. Now, finally, let me say about probably the most exciting subject, and that is the application of these ideas to coronae of accreting black holes. This is what we are looking at now with Jeremy Goodman. Observationally, we know that from fitting those spectra that I showed you in the beginning of the talk, that black holes, specifically in AGNs, have coronae that are somehow have Compton Y parameters that are derived from the spectra close to 1, and the electron temperatures kind of somewhat smaller perhaps than the rest mass of the electrons. It's marginally relativistic. And from this it follows that the Thomson optical depth of these coronae is of order 1. These are believed to be observational inferences. Well, we can try to see what it means for the actual physical parameters of the corona. when you work with accreting black holes, it's very useful to work in some dimensionless variables, in particular scaling things to Eddington luminosity and Eddington accretion rate, and distances to gravitational radius and so forth. So this is done here. M dot is the dimensionless accretion rate. Little r is radius divided by the Schwarzschild radius and so forth. Now we also need to know the magnetic field. It is believed that a fair fraction of the energy released in these systems is released in the corona. And we believe that a fair fraction of angular momentum that drives the accretion also goes through the coronal magnetic field. So if you have if little f is the fraction of torque that is transmitted by the coronal magnetic field, you can then estimate this field simply in terms of the accretion rate, simply equating the Maxwell stress with the accretion torque that is needed to provide a given mass accretion rate. This gives you an estimate for the magnetic field, and then you can express it in terms of these numbers, and you'll get an expression something like this. So the alpha velocity associated with the magnetic field is scales as the speed of light times a bunch of these dimensionless numbers to various powers. The density is simply expressed in terms of the optical depth tau, and there is a characteristic density for the corona that basically one can define, that basically is the density that corresponds to tau of order 1 on the scale comparable with the gravitational radius of the black hole. So once you do this, you can go further and compute the resistivity, the Lindquist number, the Sweet-Parker thickness, and so forth, and also the ion collisionless skin depth. And then you divide them by each other, and you see that the result is something like this. So what one should derive from this is the following. It's basically a bunch of dimensionless parameters, which we believe to be of order 1 to various powers, times this factor, that is square root of mass, electron to proton mass ratio times Coulomb logarithm, that is of order 1/10. So by and large, we actually see that these two scales are comparable to each other. If tau is of order 1, then the corona is marginally collisionless. Or you can put it differently and sort of inverse it and say that if we believe that coronae are marginally collisionless, then this is the explanation why the optical depth, roughly speaking, should be of order 1. So the basic picture to summarize all this coronal heating paradigm is that it's important to realize that there are two regimes of reconnection. The slow regime that takes place in collisional plasmas, and that's the Sweet-Parker reconnection. And then there is a fast regime that takes place in collisionless plasmas. And there is a condition for the transition between them, and that drives a cycle that maintains marginal collisionality in the corona. The cycle also includes, as important elements, the mass exchange between the surface of this star or the disk and the corona, and radiative cooling on longer timescales. Okay, so I will just say 2 words and then I'll be done. Recently, there has been a resurgent, sort of emerging interest in magnetically dominated models for gamma ray bursts, for central engines of gamma ray bursts, and also core collapse supernovae. And I wrote a couple of papers with Andrew McFadden, and we proposed the magnetic tower-like scenario driving a jet through the star. But in any of these models, it is important to address the question of whether magnetic field that is highly wound up inside of the in this central engine can survive its propagation through the star and not, say, lose its energy to reconnection. Well, it turns out that that the physical environment inside a collapsing star is so extreme that one really cannot use our intuition obtained from the solar corona, say, or even from AGNs or X-ray binaries. The main thing that is different here is the very, very high density. It is true that everything is extreme. The magnetic field is extreme, the temperatures and so forth. But it's the density that makes the difference. If you take the density that should be there, you can estimate the mean free path, of electrons or of photons. And you will see that this mean free path is tiny. It's very, very short compared with many other scales of interest. And so if you then take the Sweet-Parker thickness, you'll see that it is very small in absolute terms. It's a fraction of a centimeter. But it is much, much higher than any of the collisionless scales, the microscopical scales. So this suggests that resistive imaging does apply in these environments inside collapsing stars. And the implication of that is that there should be no fast reconnection. You can only get Sweet-Parker reconnection, which is utterly slow. So I will stop here with this summary, and I'll thank you for your interest. Questions? I know there must be questions. Andrew.
So in this picture, you have a buildup of vertical magnetic flux threading the disk itself.
In which picture?
The picture that you have, you have the flux expelling magnetic field loops.
In the disk, in the accretion disk, or in the GRBs? In the accretion disks. You don't build up net flux, obviously. You cannot produce net flux, right? Whatever comes out of the disk has to come back in. So what is the question that you?
Well, this is part of what I mean, you have to maintain magnetic fields of a given strength in the disk, right? Just to keep the turbulent dynamo. I mean, that's part of the ingredient of this is keeping the turbulence going in the disk, right? If there's no magnetic
Right. Well, this field is dynamically is subdominant inside of the accretion disk, obviously, as it is in the convection zone of the sun. It's at a fraction of equipartition with the gas pressure inside of the disk, or if it's a black hole radiation pressure, perhaps. But it is subdominant. You keep regenerating it through dynamo. That is true, yeah.
Yeah, and so what is it that regulates it to be sub-equipartition that prevents it from growing larger?
Well, that's actually a very good question. That's the question that is at the heart of determining what fraction of the energy that is released by the accretion process is dissipated in the corona versus what dissipates in the disk. And this is actually one question that I didn't address. And I cannot answer it within the model that I'm looking at. Well, the basic picture here is this. We believe that turbulence in accretion disks is driven by the magnetorotational instability, at least in well-magnetized accretion disks, where the plasma is conducting. Magnetorotational instability is interesting in the sense that the eigenmode of the MRI is an exact nonlinear solution, as Goodman and Xu showed in 1994. So what MRI does, it takes the free energy associated with the shear and converts it into magnetic energy and kinetic energy of the channel flow. So that MRI by itself doesn't result in turbulence immediately. It results in a well-ordered channel flow in opposite directions, and that amplifies the horizontal magnetic field. If you want to produce turbulence and ultimately dissipate this energy into heat, you have to understand what disrupts this channel flow. And there are several things that may disrupt it. First of all, if you have just unstratified disk, then this nonlinear channel flow, which is an exact solution, itself, it is a solution, but it becomes unstable. Itself unstable. Again, it was analyzed by Goodman and Xu. And that it's unstable to secondary or parasitic instabilities. And they cause small-scale turbulence that eventually dissipates the energy through a turbulent cascade in the disk. On the other hand, if the disk is stratified, then perhaps sometimes these channel flows, the magnetic field associated with them, it's predominantly horizontal, may become subject to Parker instability before it is disrupted by the parasitic instabilities. And in this case, a certain fraction of energy will be transported into the corona and will be deposited there and dissipated there. Therefore, the fraction of the energy that is released in the corona basically tied to the question of what is important, what becomes important first, the parasitic instabilities of Goodman and Xu or the Parker instability. And this is a question that hasn't been answered.
Sort of a simple question. When you're talking about the two different extreme regimes, the minor and low, small H field lines or the nearly open ones, how do you grow the flux tube to such a great height and faster than the orbital time shoots it out?
Well, the magnetic field in the corona is force-free. It means that it's energetically dominant. The Alfvén velocity associated with this magnetic field is higher than the Keplerian velocity. So from the point of view of the coronal magnetic field, the Keplerian shear is a very slow motion, and the magnetic field always keeps itself in magnetostatic equilibrium. It's slowly adjusting its equilibrium. And if you take a loop with a given foot point separation and in a given, say, stratified pressure atmosphere, the shape of this loop, including its height, will be determined by this magnetostatic equilibrium. And you can show that it grows as the foot point separation grows in a certain manner that is related to how rapidly this confining pressure drops with height. Does that answer your question?
How worried are you that you don't have velocity in your field, in your field loops? I would imagine that would substantially increase their cross section, right? Because as you start twisting them around.
Well, I'm not as worried about this because there are tons of things one could be worried about here. This is you have to see this as basically a very general framework. We are just developing a language for describing these things. There are many effects that perhaps should be investigated in the future, and this picture will be altered in some way. Now, in the case of the solar corona, actually, we do see that sometimes magnetic loops are twisted, and they are known as the sigmoidal loops. They look like, in projection, they look like S or inverted S. And if you twist them more, they will erupt. And this is, again, what I observed. So when you see a sigmoidal loop, it's a warning sign that there may be a flare soon afterwards. However, we don't see loops that do wild things. They may be like inverted S, but not completely huge.
How wild they look, I suspect, depends upon the vorticity of the footprint, right? So.
Well, it is determined by how much it can take before it erupts, because they.
But
right. I mean.
Slowly differentially rotating, so that means that what's causing this rotation of one footprint reduces velocity of the field.
Right.
In the accretion, as you pointed out, that's much more important. So it's entirely believable that you have such crazier things.
Well, but in the accretion disk, what you have is not sort of twisting. It's essentially linear. If you look at the patch on the disk that is much smaller than its radius, you can forget about toroidicity. It's just a linear shear.
Sure, but
In, in,
rigid body in a linear shear field, don't you spin it up?
hmm?
You put a rigid body in a linear shear field and rotate it.
Mm-hmm.
That's what's happening with these footprints.
Right, right.
So
The loop will grow. That will be the main effect, and it grows as fast as it is sheared.
Footprints are much smaller than the separation, right?
That's the assumption, actually. Yeah, that's right. That's the assumption.
I mean,
Uh-huh.
I mean, at least in the solar dynamo, of course, I mean, helicity is not a higher order question. It's a crucial feature, right? You have, in any hemisphere, only flux of a given sign. Helicity is preferentially muted. This is crucial for maintaining the dynamo. And so
Mhm.
is this something that should eventually be even zero as far as describing the disk coronae, or is it not as important as it is?
Maybe in the future. I don't know. I mean, at the moment, we are trying to figure out the main qualitative features from the point of view of what happens with the loops as they reconnect with each other, for example. Whether they have, so at the moment we neglect any internal twist within the loops. The major effect that will have actually is on the cross section perpendicular to the loops. That will affect the reconnection cross section. All right, any more?
Can I ask more questions?